Hi, welcome to es301 Engineering Analysis. Topic of this video is Chapter 6, Open Methods. So here are the learning goals. At the end of this video, you'll know the difference between bracketed and open methods for finding the root or roots of an equation. You'll understand some engineering situations where an open method is necessary when finding a root. You'll understand the fixed point iteration technique. You'll be able to implement the Newton-Raphson method, and also be aware of some of its major limitations. And you will know the secant and modified secant methods and why they might be a preferable technique. So remember, in the previous video, we looked at bracketed systems, or bracketed methods. In this video, we're looking at open methods. And so the time that you want to use open methods is when the root bounds are not known. Remember, when we had bracketed techniques, we always could know what a lower bound and upper bound was, and we knew the root occurred somewhere in between. Sometimes, though, that's not really possible. And here's just a couple examples that might come up. Here what I have, this is actually a computer simulation of the diffusion of maybe say a pollutant in the ocean over time. And over time, the area of this is going to get larger. And so what effectively you have is you have the area of this, which is some function of time, right? And so maybe you want to know at some point when that is going to be at some critical area. But the thing is that you know maybe, well, clearly it has to have, the lower bound might be time 0, but you have no idea what the upper bound might be. What is it, 1 day, 1 month, 1 year? Maybe it never happened. And so here's an example of a time when you don't really know what the bounds are. Here's another example. Maybe I'm just computing what the bending is of a beam, or maybe a very complicated structure. And so what I want to know is what the deflection is for a particular force. So I'm trying to find out what the deflection is given some force. I have no idea. I mean, is it going to be, a millimeter? Is it going to be a meter? Sometimes you just really have no idea, no intuitive feeling to be able to put bounds on it. And then here's yet one other example, is maybe you're designing a mechanical gear system and you're trying to determine the proper gear reduction ratio. And so what would it need to be? And so if you have a design specification, sometimes it's not really clear exactly what your bounds on your gear ratio could be. Is it going to be 1, 10, 1,000, 1,000,000? It's often difficult to know. Now, I recognize you can always probably bound, something from like minus 100 trillion to positive 100 trillion. But as we saw with the bracketed techniques, if your bounds are too large, it takes a long time to converge. And what we're going to see is that instead of setting huge bounds like that, open methods are just a better way to go. So I want to discuss, we're going to look at 3 different methods, or actually 4 because there's modified secant and secant, but primarily 3 different methods. And the first one we'll discuss is fixed point iteration. And so if you remember this equation we looked at from the previous video, we had this function f of x, and this was actually, we were looking at the entropy. And so maybe we were trying to find what this is, and so we were trying to find that function equal to 0. Well, what you could do in fixed point iteration, it's actually a fairly simple thing, is what I'm going to do is I'm just going to go ahead and add x to each side. So I'm going to go ahead and say that that's equal to x, and I'm just going to go ahead and add another x to the left-hand side. And you can go ahead and, that's obviously fine algebraically. And now what I'm going to do in fixed point iteration is I'm going to go ahead and take my initial guess of x, put it on the left-hand side, and then compute what that would be, and that will be a new value of x. So I'll call that x new. It's going to be something different. And then what I'm going to do is I'm just going to take that value of x new, plug it in the left-hand side again, get myself a new value of x new, and hopefully over time that's going to go ahead and convert. Right? So kind of just to get a feel for what I'm doing here, what I've done now, this is no longer f of x, right? Because I've added an x to it. It's all called g of x. It's just another function of x. It's somewhat similar. And I'm saying that g of x is equal to, well, that's equal to x. And so more or less what I have is that I can have y as a function of g of x, and then I've got y is equal to x, right? Just 2 different functions that I'm trying to find out where they are equal. And so kind of here's what's going on. And so let's look at this left-hand diagram here first, is I have my initial value of x called x naught. And so this line right over here, this is my g of x line. This is the one that's the function that I have plus an x value. I'm going to go ahead and calculate what its parameter is. And then what I'm doing is I'm saying, well, that's going to be equal to the value of x. That's x new, which is just this y of x line. And then what I'm going to do is go ahead and use that value of x to go ahead and find my new value of g of x, and then set that equal to x. And so you can realize is that hopefully over time you're going to just step right down to the point where those two lines cross, which means I've now found a solution to find the value of x. So this is the point when it's going to go ahead and converge. But what happens with this method, it can happen with most open methods, is it can diverge. And so what I can look at, let's go ahead and look at this one down here on the bottom. If I start up at this value of x naught and I go up here to my line of g of x and come over and set my value of x to that and keep going, since I initially overshot it, it's going to eventually go off into infinity and I'm not going to converge. Here's another instance where that could happen, where I've got two different slopes. So this again is my g of x line here that I'm trying to find. If I start here, assign that value to x, compute my new g of x, and you can realize that this is going to go ahead and diverge with time. And so fixed point iteration works sometimes, but not always. And it really depends on the shape of the function. And so it's kind of difficult to know necessarily what the shape of the function is ahead of time. It's more likely to converge the closer that your value, your initial guess of x is to the proper one. But again, that's somewhat hard to know. So fixed point iteration, easy to implement, but does have the caveats of when it can diverge. So let's go ahead and look at another technique. It's a little bit more commonly used, and it's also tends to converge faster when it does converge. It's called Newton-Raphson, and not surprised, it's named after people. Over here, this is Newton on the right, and this is Joseph Raphson over here on the left-hand side. And they look kind of spookily similar, which I think was just a function of their fashion at the time. Kind of glad that fashion went away. But anyway, so what we're doing with Newton-Raphson is, okay, so imagine, let's look at this function I have drawn over here. And what I want to do is I'm trying to find out where this function is equal to 0. And so what I'm going to do is I'm going to take my initial guess. Maybe I'll take that point right there. And then what I'm going to do is I'm going to calculate the derivative of that. So extend it down to the axis. And that will be my new guess of x. And then I'll go ahead and again find out what the value is and its derivative. And then plunk it down there. And hopefully I'm going to eventually come down to where I find the root of my equation. And so this is my initial guess. This is my next guess, and my next guess as I move around. And what you realize is this tends to converge fairly quickly, particularly for monotonic functions. All right. So the formulation of this, well, this is how I'm going to find my new value of guess of x, my new x, my x new, which is x of I plus 1. I take my initial value of x, and then I've got my function, and on the bottom I have the derivative. And recognize all I'm doing there is I'm saying essentially the function is more or less equal to the derivative times delta x, right? So df dx times delta x is more or less the value of the function. And so that's where that term comes from. So it gives me some sort of feeling for what the new value of x is. And this technique tends to converge fairly quickly for monotonic functions. However, there's sort of a caveat here. You have to be able to calculate both the function value, this value of f at the top, and you also need to be able to calculate the derivative. And so it's kind of simple for straightforward algebraic equations like we showed in the previous slide. But a lot of engineering applications, that isn't necessarily easy, particularly for complicated models. Let me just give an example, one from actually some work that I've done in the past, which was looking at the dispersion of volcanic ash with time. And so if you look here, just to kind of let you know, this is Iceland right up here, and this is Europe over in this region right over in here. And this is an eruption from Mount Etna. And so this is kind of showing the concentration of ash with time. And so what I imagine, I want to know what the area of this ash cloud is as a function of time, as it disperses. And maybe what I want to do is I want to know when it is some particular value, right? So again, what is the area, some critical value that the cloud is at? Well, the thing is, I can go ahead and plug in all the physics into my model and calculate the area. But it's not really easy to know what sort of the derivative of the area is, because this isn't a simple algebraic function. I got to bring in wind data and particulars of the ash cloud distribution size and these types of things. It's not just a simple algebraic equation. So it's not necessarily easy to go and determine what that is. And recognize area is a function of time, right? It's just kind of like, there's my value f, which is a function of x. So Newton-Raphson wouldn't work particularly well for this, because I don't have an easy way to go and find out what the derivative is. There's some other things that you need to be careful with Newton-Raphson. There's several times when Newton-Raphson can fail. So although when it works great. When it doesn't, it can fail spectacularly. So here's a couple examples. And so if we look at this top diagram, this is from the book. If here's my initial value of x, I'm going to go up to my function, calculate that function value, and the derivative. Remember, I extend that down to the axis, and then I go ahead and do that again. Well, what you realize, if I have a function that looks like this, and I keep doing that, well, the way that that similar looking function, this is an instance where it's going to go ahead and diverge. Here's another example where it doesn't work. And again, as I said, this tends to happen when you don't have monotonic functions. So I start at my x naught, I'm right there, go up, and I'm going to go ahead and take my derivative, come down to the axis, and you realize I start bouncing around, go up, bounce, and then I get to the point where I'm almost at a flexion point, and I start to diverge away. And so again, it takes a lot of steps, and then it eventually just fails on me. And then, this third example is yet another example of where, since I've got multiple roots, it's actually skipping what it is. It goes up and then over, and then it skips completely over both of these roots that I have. In fact, there's one over here as well. So remember, this is a non-monotonic function, and this is where Newton-Raphson tends not to work too well. And yet, here's the bottom here. Yet one more example where it fails, because anytime it comes down pretty close to something where you've got a derivative that's close to 0, the point's at 0, you're going to get quick divergence away. So yet again, another instance where Newton-Raphson fails. So you need to be careful when using that. There's a lot of instances where it can fail. One way to monitor that, if you write a Newton-Raphson routine, is monitor your error. And so remember this, the approximate error is the value your guess normalized by your previous guess. And what you want to do is make sure that that's not growing with time. And if it starts to grow very quickly, maybe you're running in this instance where the solution technique is divergent. All right, let's look at another method. This is the third method we'll look at. It's called the secant method. So let's just remind you what a secant is. If I have my function shown here in blue, and the tangent, here's my tangent line, it would be a derivative. A secant is more or less a slice between 2 points, and so that's shown in red. So I'm given 2 points, this line that connects those two. That's what a secant is. Right? And so the way that the secant method works is, imagine here's my function that I want to go ahead and find the root of. And if this was my initial guess, first of all, if I did Newton-Raphson, right, I would take the derivative, and then I would go ahead and try to find the function at this value. And in fact, it kind of shoots off into infinity, or it may not even be defined. So there's a point where Newton-Raphson would fail. But secant, what we're going to take this point, instead of finding the derivative, I'm just going to take some other starting point. I'm going to draw the secant between them, extend that down to the y-axis, and there's going to be my new value of my new guess. And then I'm going to come up to that point, use these 2 points, and move down, and hopefully I can go ahead and find the root. So here's a point where secant method would work, and Newton-Raphson would go ahead and fail. So if we just look at the way, here's some equations from the textbook. Again, what I've done now is, here's my derivative. I'm approximating as just the rise of the run, my function value at 2 guesses. This one over here is I minus 1, and this is I, and then I'm looking for I plus 1. So first of all, I went ahead and just determined what the derivative is at those 2 points. Here's my equation from Newton-Raphson where I have the derivative, so I'm going to take this derivative and plug it into there. So I'm more or less eliminating the derivative term. And here's what my new value of x is. This is that third value that I've got, x of I plus 1. And so it's a function of, I evaluate my function at xi, and I do it at the previous one. And that's all I need to do is just evaluate the function. And so this is a lot better, like for example in that area method where I had before, I don't have to go ahead and find the derivative of the function. Let me mention one other thing though. There's a modified secant method. And the reason you might use the modified secant method is that sometimes it's even difficult to determine 2 initial guess values. So in my secant method, I had some initial guess x of I had some value x of I minus 1. And what I wanted to do is use those 2, but I need 2 initial guesses. And that isn't always necessarily really easy to do. And here's just an instance. I'll just come back to this volcanic ash dispersion model idea where, for example, this model can give me the area of the cloud as a function of time, and I want to know when it is some critical value. So maybe I'll pick my first point, which would be, I don't know, 1 day, which I have no idea if that's even close. And then what would be my second one? Should it be a day later, an hour later, a month later? Sometimes it's really difficult to know even what the second time is. So what I could do is just go ahead and do what's called the modified secant method. So remember, here's what this came from the secant method, where I've got what my derivative is. And instead of having 2 points, my I minus 1 and x of I, I'm just going to go ahead and make this some small value delta xi from what x is. So for example, if I had my initial point was 1 day, I'm going to go ahead and add 1 hour to that. So delta would be 1 hour relative to 1 day. And then this down here will just become delta xi, the difference between it. So instead of knowing 2 points, I'm just kind of taking some small amount, but I'm not necessarily evaluating the function at it. And if I go ahead and do that, here would be my modified function, my modified secant method. Here's my new value of x of I. And the thing that's different now is I'm only evaluating my function at 1 point, f of x of I, and then I'm using this delta value. So it's a little simpler. I don't have to evaluate the function twice. I just evaluate it once, and then I have some sort of parameter that I'm trying to determine, which here would be delta. So there's kind of an example of when you might use modified secant over secant. They're very, very similar. All right, so let's just go and review what we looked at in this video. First of all, we discussed open methods, and we saw that they're used when the roots cannot be bounded initially, or at least bounded with some sort of same values. One caveat, open methods have the danger of diverging. One thing about bracketed methods is they don't tend to diverge. We looked at fixed point iteration. We saw it's fairly easy to implement. It converges somewhat slowly, and it can diverge, as all open methods can. We saw Newton-Raphson. It can be fairly efficient, but it does require being able to find the derivative of the function. So it's not always useful if you said your function is difficult to find the derivative of. And Newton-Raphson can diverge, and when it does, it's fairly spectacular. And it tends to happen when you have these non-monotonic functions that you end up with that problem. Then we looked at the secant and modified secant methods. We saw that they're efficient as long as you can determine the function fairly efficiently. So you don't have to do the derivative, but you've got to calculate the function a couple more times. So is it easier to calculate the function or calculate the derivative would be the trade-off between those two methods.